Let us look at proposition number 11 of book 12 of Euclid's Elements. The proposition says cone and cylinders of the same height are to one another as their bases. So we have cones and cylinders of the same height with their bases A, B, C, D a circle and E, F, G, H as circle. K, L and M, N are their axes and AC and EG are their diameters. So AC and EG are their diameters. Now what the proposition is saying is that circle ABCD is to circle EFGH is equal to the cone AL is to cone EN. Cone AL is to cone EN, we are talking in terms of volumes. So whatever is the ratio between the base of this cone and the base of this cone will be the same as the ratio of the area of this circle and the area of this circle. So again, we are going to use proof by contradiction. So if not, circle ABCD is to circle EFGH as cone AL is to some solid which is not equal to the cone EN. That means either it is less or it is greater than the cone EN. So let that solid O be less than cone EN. So volume of the solid O is less than the volume of the cone EN. Let solid X be cone EN minus solid O. The difference between the volume of the cone and the solid O. Let it be a solid X. I have not drawn that. So cone EN will be equal to solid O plus solid X. Now inscribe the square EFGH in the circle EFGH. So let's do that. Now, which means square EFGH is going to be greater than half of the circle EFGH. Now, set up from square EFGH a pyramid of height of the cone. So this pyramid would be a pyramid with a square base. So let's do that. Now, which means pyramid on EFGH is greater than half of cone EFGH. Now we bisect the circumferences EF, FG, GH, HE at PQRS. Let's do that. And we join these points. So each of the triangles HPE, EQF, FRG, GSH is going to be greater than half of that segment of the circle about it. On each of these triangles, HPE, EQF, FRG, GSH, a pyramid of equal height with the cone is to be constructed. So let's do that. So that means each of the pyramids that we have, HPEN, EQFN, FRGN, GSHN, is going to be greater than half of that segment of the cone about it. As we have seen in previous propositions, we keep repeating this process of bisecting the circumferences, setting up pyramids, etc., and doing this repeatedly so that at some point remainder would be less than the solid X. For simplicity's sake, let's say those segments HP, PE, EQ, QF, FR, RG, GS, and SH. So the remainder, the pyramid with the polygonal base HP, EQ, FR, GS and the same height as that of the cone is greater than solid O. inscribe in the circle ABCD the polygon similar and similarly situated to the polygon HPEQFRGS. So let's do that. And then we set up a pyramid of equal height with the cone AL on this polygonal base. In one of our previous propositions, we saw that polygons are to each other as in the duplicate ratio of their diameters. And here AC is the diameter of the polygon DTAU BVCW and EG is the diameter of the polygon HPEQFRGS. But we have also seen that circle ABCD is to circle EFGH as the duplicate ratio of the diameters. So, which means circle ABCD is to circle EFGH is equal to polygon DTAU BVCW is to polygon HPEQFRGS. But we also have this starting point. Circle ABCD is to circle EFGH is equal to cone AL is to solid O. We also know that pyramids on polygons are proportional to the polygonal bases. Polygon DTAU BVCW is to polygon HPEQFRGS is equal to pyramid on DTAU BVCW is to pyramid on HPEQFRGS. So cone AL is to solid O is equal to the ratio of the circles, and circle ABCD is to circle EFGH is again equal to these polygons. And on those polygons, we have constructed the pyramids. So which means cone AL is to solid O is equal to pyramid on DTAU BVCW is to pyramid on HPEQFRGS. Alternately, we can say cone AL is to pyramid on, or let's say pyramid in it, is equal to solid O is to pyramid in cone EN. Now, since cone AL is greater than pyramid in it, implies solid O is also greater than pyramid in cone EN, which is a contradiction. Since solid O is supposed to be less than cone EN. So, because of this contradiction, circle ABCD is to circle EFGH is equal to cone AL is to a solid less than cone EN is not possible. We have shown that this proportion will not hold if a solid is less than cone EN. Now we have to look at the other case where a solid is greater than cone EN. So let's look at that. If possible, let solid O be greater than cone EN. So inversely we can say circle EFGH is to circle ABCD is equal to solid O is to cone AL. Now solid O is to cone AL is equal to cone EN is to a solid less than cone AL. Basically what we are doing is we are converting this proportion in such a way that we get the first case. And first case we have already shown. So circle EFGH is to circle ABCD is equal to cone AEN is to a solid less than cone AL, which we have already disproved in the previous case, which is impossible. So circle ABCD is to circle EFGH is equal to cone AL is to solid not greater than cone EF. So that means circle ABCD is to circle EFGH is equal to cone AL is to cone EM. Now, once we have shown this with respect to cones, cylinders are pretty straightforward, because in our previous proposition, we have already shown that cylinder is 3 times the cone and cylinder is to cylinder is equal to cone is to cone. So, which means circle ABCD is to circle EFGH is equal to cylinder on ABCD is to cylinder on EFGH with the same height as that of the cone, or rather both having the same height. So that is proposition number 11 of book 12 of Euclid's Elements. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.